Hi everyone, my name is Thomas Kim. Today is December 28th, 2019. This is my 65th episode about linear algebra and threading building blocks. On October 19th, 2019, I started this journey into the linear algebra and threading building blocks. Since today is December 28th, almost 70 days has passed. After this episode, we will complete 90% of our first journey into the linear algebra because we implemented our Matrix 2D class to support not only real numbers but also complex numbers. In future, we can implement QR decomposition and singular value decomposition. In this episode, we will implement optimized inverse permutation and product over permutation and matrix. Product over permutation and matrix is much more efficient than the product over permutation matrix and a matrix. This episode continues from my previous episode, episode 64. If you haven't watched my previous video, please watch it by clicking this link. Also, you should have watched episode 63, episode 62, and episode 61. Scroll down. In the download source code section, please double click this link, show in folder, unzip it, rename 65 Optimized Inverse Permutation. Copy the folder, paste it to your working directory. This is my working directory. Start Visual Studio Code. Open the folder, expand folder 65. Double-click matrix2d.hpb. Ctrl-B, Ctrl-F, find inverse. This is not very optimized. I would say deprecated. Copy once again, copy, paste, rename it, just inverse. We don't need this part. This is not create unit permutation. Allocate memory. For size ti, I less than p size plus I would say k. P equals k, this k. Now Ctrl F, end of class matrix 2D. Here print matrix 2D operator constant permutation TBB. Constant matrix 2D M. Pre-multiplication swaps rows. If debugging equal 1 and if PB size is not equal to M rows, talk play fun, throw debug exception, invalid operation. PB size should be equal to M rows. Matrix 2D row swapped. M rows, M columns. For size T, I less than M rows plus I. For size T, J less than, I would say P swapped columns plus J row swapped IJ M PV I J swap row I with row PV I. Return row swapped. Post multiplication swap columns. Print matrix 2D operator constant matrix 2D M constant permutation T PB if debugging equal 1 and if PB rows not equal to M columns talk play fun throw debug exception invalid operation PB rows it should be size should be equal to M columns matrix 2D column swapped M rows M columns for size TI I less than column swapped rows plus I for size TJ J less than column swapped columns column swapped IJ equals M I PB J return column swapped. Sorry, I made a mistake here. It should be debugging mode. Also, it should be debugging mode. Now, find Ctrl F proxy class. Here, we will implement two functions. Constant permutation T L value reference row permutation constant no except I will indent a little bit return this M row permutation copy once again copy paste column permutation it should be column. Now let's test open explorer permu Ctrl V copy this path copy paste we will change the function name Permutation-Matrix Product copy the function name paste it here disable this path size T row count column count make it 3 it should be 4 I will post this script in the description section below you can copy this text and paste it here matrix T A row count column count or you can use curly brace too like this. Now we print out the matrix first output print matrix stream A 6 stream A and there. Now start command prompt dir cd 64 optimized inverse permutation clang std c++17 permu.cpp ltbb malloc hit enter 2192 Ctrl G 2192 I made a mistake here M columns build again so this is our initial matrix we will swap two rows row 0 and row 2 this is row 0 row 1 row 2 we will swap two rows then we will swap columns like this permutation T this should be row count or A rows. Permutation for pre-multiplication to swap rows. Permutation TQA columns. Permutation for post multiplication to swap columns. or P matrix T permutation, we provide P. P is a permutation matrix created using permutation P. or Q matrix T permutation Q. Q is a permutation matrix created using permutation Q for swapping rows, for swapping columns. Okay, now here P swap elements 0, 2. Swap first row, its index is 0, and the third row, its index is 2. Q swap elements 0, 2. Swap first column, its index is 0, and the third column, its index is 2. Now stream row permutation matrix P, and there output print matrix stream P6 column permutation matrix Q. Here stream P Q row permutation. This is column permutation. Now let's build what happens. CLS. So this is original matrix. I will put a line break here. CLS. So this is original matrix. This is row permutation matrix. It means we are swapping first row with the third row. In this case, we are swapping first column with the third column. So we generated row permutation matrix. First row, this is third row. This is first row. This is first column. This is third column. So, or B, you can say P multiply A Q. Swap first row and third row. Then swap first column and third column using permutation P and Q. Stream P equals P A Q. And there output print matrix stream B6 or BB P A Q. I will copy this part, cut, paste it here, and paste it here using permutation matrix P and Q. Why is squiggle? Okay, I missed one. Also here, this is BB. P, Q, BB. Now let's run it. CLS. So this is row permutation, column permutation, matrix Q. P, A, Q. We are using permutation PQ. Then this matrix is transformed like this. Row 1 and row 3 are swapped. Then column 1 and column 3 are swapped. This is the result. And this is the same result. In this case, it uses permutation P and Q. In this case, permutation matrix P and Q. Now we can restore or C P inverse times B times Q inverse. C equals inverse P times B times inverse Q. Restore B to A or CC P transpose times BB times Q transpose. CC inverse of P times BB times inverse of Q. Restore BB to A. Inverse of P equal to transpose of P, because P is an orthogonal matrix. Now we display. I will copy this part. Copy. C P inverse A Q inverse C. I copy once again. CC P inverse Q inverse CC. Command prompt again. CLS. So from B we restored to original matrix A. From BB we restored to original matrix A. Understanding this operation is very important for Gaussian elimination algorithm and Gauss-Jordan algorithm. If you don't understand this part, Gaussian elimination algorithm, Gauss-Jordan algorithm are useless. I made a mistake here. It should be B and it should be BB. If you don't understand this episode, that means you haven't watched my previous episode, especially episode 61 and episode 63. If you watch episode 61 and episode 63, you understand my current session. We implemented most algorithms for Gauss elimination algorithm and the Gauss-Jordan algorithm, lower triangular matrix and upper triangular matrix, LU decomposition, LDU decomposition for partial pivoting, scaled partial pivoting, and complete pivoting. I haven't implemented complete pivoting yet, but I will implement in my next episode or the episode after next episode. I think we completed more than 90% of our initial adventure into linear algebra. In near future episode, I will optimize my algorithms and clean up some code. Then in some distant future, I will implement more algorithms in linear algebra, such as inner product space, also QR decomposition, also singular value decomposition, and the matrix with polynomial entries, and eigenvalues, and eigenvector, etc. Please subscribe to my YouTube channel. Thank you for watching.